Hi, my name is Josh Becker, and today I will be discussing real-world industrial plant power factor penalty and correction. So, we will start by talking about what is the power factor. The power factor is a ratio of real power to apparent power, where real power is measured in watts and apparent power is measured in volt amps. And to describe this, I like to use the beer analogy. As you see over here on the right, we have a beer glass, and let's say this beer costs $5. If we have a lot of foam on top, which can be considered the reactive power, we will not be happy. But if we have more beer and the beer goes up to the top, that acts as real power, and the more beer we have, the more bang for our buck we get. So, a high factor means that most of the apparent power is doing work, which means most of the apparent power is real power. If you have a low power factor, this means that more apparent power is not doing work, which means we have more reactive power. However, reactive power is needed to magnetize some loads, such as electric motors or transformers, so reactive power isn't a total waste, and it's not completely lost power. Now, what are some effects of having a poor power factor? Poor power factors are usually less than 0.9, 0.85, 0.8, kind of depends on who you're talking to and what we're talking about, but there are still some common effects. And one of the common effects is a poor power factor leads to the need for more apparent power, because as we know, power equals voltage times current. So if we keep the voltage the same and we increase the apparent power, we then have to increase the current, and with more current we need larger lines, larger cables, and more expensive equipment. We also see more losses when we have a poor power factor. Loss will be seen in transformers, and we will also see voltage drops in the distribution system. Utility companies charge for a low power factor, which is the power factor penalty, and they charge for it because more current is needed and more expensive equipment is needed because the current is higher. So power factor correction. So in industrial plants, most loads are inductive, which means they are motors, which is true for most plants. To counteract the inductive loads, we're going to use the opposite of an inductor, which is a capacitor, and you can install capacitor banks right before the load, or you can do it in the beginning of the distribution system. It's usually most effective to put the capacitor right before the load. However, if you don't know which load is causing the power factor to be bad, or there's more than one load that is causing the power factor to be bad, you can put the capacitor bank in the beginning of the power system. Harmonics. This kind of describes the power and the quality of the power. If we have clean power, that means there's no harmonic distortion, which means we have pure sinusoidal waveforms for current and voltage, which means the power is also going to be a nice clean sinusoidal form. If we have dirty power, that means either the current or voltage waveforms is distorted, which means the power is also going to be distorted, and this causes some issues, as we can see in the lower right. Current harmonic distortion problems. Let's see, on motors, it will reduce the motor life and inability to fully load the motor, and motors are usually the load in industrial plants. There's also transformers in industrial plants, and that's going to increase losses and reduce capacity. And fuses and breakers are in every distribution system, and it will damage those components as well. Voltage, harmonic distortion problems can lead to mechanical fatigue and eventually failure in motors, and then in transformers, increased noise and possible insulation failure, as we see there. So what causes harmonic distortion, that's going to be nonlinear loads such as PLCs, which are programmable logic devices, or variable frequency drives, VFDs. These used to not be common, but with today's technology, they are becoming more and more common and more used. So to correct the harmonic distortion, a harmonic filter can be used, and that can be attached to the capacitor bank. As we can see on the top right, we have the capacitor bank in a Y-connected three-phase system, and then in each phase we also have a harmonic filter, which will filter which will reduce the harmonic distortion. So now we're going to look at some real companies' electric bills and see how they were charged for their power factor. Company X requested not to be named in the project, so we will refer to them as Company X. Company X got their bill in February 2019 that they provided me with, and their total charge was $66,217. The energy charge came from three main components, which was the energy charge, the demand charge, and credits. The energy charge was the total consumption of real energy, and that was charged per kilowatt hour. The demand charge is what penalized Company X for their poor power factor. So during February 2019, Company X had a power factor of 79%, or 0.79. And as we can see, the equation below, the power factor penalty equals metered kilowatts minus the bill demand times the rate, which is 13.78. Bill demand is just metered apparent power times 0.85, which is 0.85 is the desired power factor by the utility that provides them power. So that's why they use that number. And then the power factor is penalized in the demand charge because as the metered apparent power increases, then the reactive power will also increase, which means that the power factor will be decreased with more reactive power. And as we can see, for February 2019, Company X was metered at 1,992 kilowatts, and bill demand was 2,144, and this led to a power factor penalty of $2,089 for the month of February 2019. Company X also provided me with some power factor information from that same plant from May 2016 to April 2017. They kept track of this information because they were actually doing a power factor correction project, and they wanted to see what they needed to do. So as we can see here, the average power factor penalty, which we can look at the right, if the average is about $2,500, which is quite a bit if you're talking about that per month. And then the power factor average for that year was 0.773, and we can see all the other metered and calculated components of their power usage during that time. Richco Structures was the other company that sent a real electric bill. They were charged by 5 different main charges. The first charge was the high energy charge, which is the energy used at night and at weekends. This is like peak times when people are home and most energy is used, so companies charge a little more during these times. And these times for Alliant Energy was 5 p.m. to 9 p.m. during weekdays, and then during the day on weekends. The regular energy charge was energy used during regular business hours, and the low energy charge was the charge for the energy used from 11 p.m. to 6 a.m. when the demand is very low, so therefore the cost is going to be a little less. Now the on-peak demand was billed by kilowatt, and the on-peak demand is the max demand during on-peak hours, which is business hours and weekdays um, from 6 in the morning until 9 at night, and during weekends as well. And again, that's charged per kilowatt. And then the customer demand charge is the measured max demand billed per kilowatt. No, excuse me, I said that a little wrong. The customer demand charge is the measured max demand that Bridgeco structure saw during that month, and that again is billed per kilowatt. Now, Alliant Energy charges customers for a power factor that's lower than 0.9, and Richco Structures was not charged a power factor penalty, which means their power factor was greater than 0.9. Now, I am not sure if they have a power factor above 0.9 because they have included some power factor correction, or if it is because their load is just has that high of a power factor. However, if their power factor was lower than 0.9, the billed reactive energy or the power factor penalty would have been billed according to this equation, where we have reactive power times the time minus the kilowatt hours times this constant of 0.484. Now, Richco Structures did not need to correct their power factor since they were being charged for it, but Company X did have to correct theirs if they wanted to reduce costs, and they want to have a power factor of 0.85 lagging or higher, because in 2011 they actually had a power factor correction project that they embarked on, and they increased the power factor to 0.85, and that's what they're charged for, is a power factor of lower than 0.85. So to get this power factor of 0.85, some quick calculations will show that Company X needed capacitors to supply 496 kilovars of reactive power, and by supplying, Company X would need to supply about 500 kVAR in order to decrease the amount of reactive power absorbed, and the real power would remain constant. And with that shrinking reactive power, the apparent power will then shrink, and then the ratio of real power to apparent power will then increase to a value closer to 1. In order to get an increase of about 500 kVAR, Company X needs to include a 3-phase Y-connected capacitor bank at the beginning of the distribution system. I said at the beginning because I'm not sure what kind of loads they have, or they could place capacitors in front of some loads if they know that the loads are bad, but I was not provided with that information, so my solution would be to connect the capacitor bank at the beginning of the distribution system for Company X. They're actually going to need 2 capacitor banks because I could not find capacitors with a capacity of 500 kVAR divided by 3. So each capacitor bank would have a capacity of 250, and then each capacitor itself inside the 3-phase capacitor bank would have a capacity of 83.3, but again, you can't find a capacitor with that kind of capacity, so we rounded up to 85 to ensure that the power factor desired was met, and using the 85 kVAR capacity for each capacitor, that led to a 510 kVAR supply by the capacitor bank, which then increased the power factor to 0.866. Below we can kind of see the description of the power factor and the reactive power consumed, and the average for each before the before the capacitor bank was added. So this was the information company X provided me with. So 0.773 as the average power factor, and they consumed 1,731 kVAR on average for that year. And the average after my proposed solution would have a power factor of 0.866, which again is above the 0.85, and the reactive power consumed decreases because we supplied 510 kVAR with the capacitor bank, and that's going to decrease to 1,221 kVAR. And with that solution, company X will meet their desired power factor, and they will be charged less, or not charged at all, for having a poor power factor. So that is some basic information and on power factor penalty, and correction, and how it can be applied to a real industrial power plant. Thank you for listening, and I hope you guys have a great day.